Today, I'm going to talk a bit about Apache Kafka and security. Apache Kafka is a very powerful and flexible platform for event streaming. The use of event streaming often grows to every corner of the organization, and this means that sooner or later it will handle event data that is considered sensitive or confidential. This is where the security setup of your deployment becomes very important. Kafka offers a lot of configuration options regarding security at both cluster and topic level. But with all of these options of Kafka, the question that we need to ask ourselves is, did I miss something? The generic nature of this question brings another fact into focus. Security itself is already a generalization. It consists of very different subjects that handle different aspects of security. To make sure that I capture most requirements for securing a Kafka cluster, I usually split it into four different subjects: communication security, authentication, authorization, and message security. I will handle these subjects one at a time, and at the end, I'll have a final note on how to combine them. Communication security is the part of security I usually start with because it's a fairly standard and straightforward subject with Kafka. What do I mean with communication security? Simply put, it's the way how the communication between the client application and the Kafka cluster is set up and secured. If event data is sensitive, then we don't want every system on the same network as the cluster to be able to capture data while it's in transit. Kafka supports transport layer security, or TLS, to make sure that the data that is transmitted is encrypted and that the client application can verify that nobody is impersonating the server. There are several versions of TLS, and Kafka supports the latest version, 1.3, since Kafka 2.5. Kafka allows us to specify which TLS versions are supported and which version is used by default. We can also specify the cipher suites that are supported, allowing us to use TLS settings that match the capabilities of the client applications. Authentication in Kafka is about determining the identity of connecting clients. Kafka has several ways of authenticating clients. TLS client authentication, or mutual TLS, can be activated as part of the TLS configuration. This requires connecting clients to provide a certificate signed by a certificate authority that is trusted by the Kafka cluster. The cluster can then extract the distinguished name or parts of it from your certificate to function as the principal name for the authorization phase. Kafka can also be configured to use SASL, or Simple Authentication and Security Layer. This is a standard framework used for authentication on Internet protocols. TLS can be activated on top of SASL as well to make sure that the data cannot be read by other systems on the network. The Kafka SASL implementation supports several mechanisms which can be enabled in parallel. Plain, which is based on a simple clear text username and password exchange. If you use the default implementations, all users and passwords need to be defined in the cluster configuration files. SCRAM, or Salted Challenge Response Authentication System. This is a more modern password-based authentication mechanism where the passwords are never stored or exchanged as plain text, but salted and hashed using either SHA-256 or SHA-512. OAuth Bearer. This allows you to use an OAuth 2 framework for obtaining and verifying authentication tokens. The client application and the Kafka cluster both need access to the OAuth 2 framework at all times for this to work. GSS API, or Kerberos. Kafka can use an existing Kerberos server to handle authentication of clients. Each broker in the Kafka cluster needs to be registered in the Kerberos server, as well as the client applications. Kafka SASL implementation supports customizing or externalization of these mechanisms. The libraries with those implementations need to be in the Kafka class path before setting the callback handler configurations in the broker configuration file. Authorization is the part of security about determining which operations a connecting client are allowed to perform and which operations are denied. Kafka allows customization of the logic by setting the authorizer class name in the construct configuration. The default implementation is provided by the ACL authorizer class. This class is based on access control lists. An entry or rule consists of 7 parts. Principal name, this is the name that the authentication implementation provides as the identity of the client. A resource type, like a topic or a consumer group. A resource name, this is the name that needs to match with the actual name of the topic or group. A type, and that's the mode of matching. You can either have literal matches, that matches the full resource name in the ACL, or it can be in prefixed mode, where the topic or group name needs to start with the resource name specified in the ACL. An operation like read, write, create, describe. A host, which means the network or hostname that the client is connecting from. This allows you to give access or deny access based on location. And an ACL type, which specifies if this rule is meant to deny a specific operation on a resource or to allow it. This default ACL approach gives us a good way to get a fine-grained access control. Just don't forget to disable the construct configuration that allows everyone access if there are no ACLs found for a resource. And don't forget that the brokers also need specific access entries as well to communicate with each other. This is usually solved by setting them as a super user in the construct configuration. The fourth and final subject I examine is message security. I usually handle 3 parts of message security: access to the data as it's stored on the brokers, establishing producer identity, and integrity check of the record content. Kafka persists the record data it has received to disks. And this means that anyone that has access to the disk could read this data. Kafka itself doesn't offer any encrypted storage, but relies on the operating system to encrypt the storage drive if needed. Most of the operating systems or cloud providers have their own implementations to provide this functionality, and it is a good practice to investigate the advantages and disadvantages of each of these implementations. The second and third part of message security, determining the producer identity and the integrity check of the content of a record, can be important to a lot of organizations. A common approach is by using signatures, which use a producer-specific key to generate a signature which is attached to the message. The consumer can verify that the contents of the record has not changed by using that information. Kafka does not support this out of the box. If you need this, you need to develop or install and deploy a third-party implementation that can add the relevant information to the producer record and verify the message content and signature at the consumer side. Final note, Kafka supports multiple listeners. A listener is basically a process that listens on a specific port, and each listener can have its own configuration regarding TLS and authentication. This allows us to create listeners for external networks with different TLS and authentication options, while also having a separate listener for internal networks, which can use internal authentication mechanisms like Kerberos. The authorization model does not change per listener. So these were the security options of Kafka in a nutshell. If you have any questions or remarks, respond to this post and I'll see if I can answer them. Thanks for joining.